Hello, in today's video I'd like to discuss a type of structure with you that I come across regularly in the support of SOFiSTiK. Users frequently ask how can I eliminate the high peak bending moments over the supports or at the vertical walls. So I would like to show you some tips and tricks how you can smooth out or at least reduce the peak bending moments over the columns or at the vertical walls. Sometimes in these bridges pre-stressing is also used, but sometimes they are just simply without pre-stressing depending on the span length of the bridge. I'd like to emphasize that the workflows or tips and tricks that I'm about to show are based on my personal experience and they are not following any official workflow. Without further ado, let's jump or dive into the problems. So I try to zoom in and show you the three areas that are problematic usually during the design of the quad elements. The first problematic location could be the intersection of the vertical wall and the wing wall. At the vicinity of the intersection, the internal stresses of the quad elements could be so high that the design is not possible, and an error message might be triggered stating this. The other problematic area could be the edge between the vertical wall and the bridge deck, since from the vertical and horizontal deflection or displacement of the bridge deck, extremely high internal forces can occur in the vertical wall that makes the design of the vertical wall impossible again. Finally, the third location where problems can occur is at the intersection of the vertical column to the bridge deck. Usually the users define absolutely fixed or very rigid point-to-point constraints between the column head or column end and the bridge deck. If I open the dialog box of this constraint, you can see that this is a constraint between two structural points and it is constrained in every 6 degrees of freedom, so it's an absolute rigid connection. Due to this rigidity or high stiffness value, this location of the bridge deck will attract much more internal forces than other parts of the deck. And since it's happening in a very small area, namely at a structural point, a singularity will be formed in the bending moments, and the quad elements cannot be designed against these very high bending moments. Let's try it out now. I have generated two load cases. In load case 1, a plus 20 degrees temperature change was applied on the bridge deck, and in load case 2, a 50 kN per square meter vertical load was applied on the bridge deck. And in load case 11, I have applied the curvature load from the pre-stressing on the structure. After having exported the system to the database and run the linear analysis, I superimposed the results of the load cases. Then I defined the parameters of the area elements in terms of reinforcement, and then try to run the design of the quad elements in the UL state. And as you can see, and I expected, I run into several errors, and mainly it is about elements have been undesignable according to the code. Results are stored in the database for graphical check. So let's see these problematic areas in WinGraph or graphics. In graphic you can represent the design of the quadrilateral elements and show the reinforcements and especially the design error in the reinforcements. A field area type of representation can be seen on the screen, and the corresponding legend can be found at the top area of the A4 page. The dark blue parts are marked with letter B, which stands for bending design, the quad elements that are marked with green color, and there is a letter S next to the green color, are failing against shear. The quad elements that are marked with B plus S and highlighted with red are failing both against bending and shear. If we zoom in to a location where a column head meets the bridge deck, you can see the highlighted quad elements whose design is not possible. When the software refers to as the design is not possible, it means that in most of the cases the compression limit stress of the concrete is exceeded. Okay, now let's go back to SOFi Plus and let me show you one or two tips and tricks to get rid of these problems. In SOFi Plus, one can see that I use two types of cross-section for the columns. A circular shaped cross-section with a diameter of 800 mm and a rectangular shaped cross-section with the dimension 600 by 800 mm. All we need to do is disperse the high reaction force from the column, and this is exactly what I'm going to do with the help of newly created structural lines. Therefore, I drew two half circles, and I'm going to assign structural lines to these half circles. The way how you can do that is simply click on the structural line command, and without any cross section I'm just going to give a group number equal with the group number of the bridge deck, and I'm going to use the pick lines or curves type of definition and select the two half circles, 1 and 2. Then I will terminate the command by escape. And now the next step is to change this fix point-to-point constraint to springs between the two structural lines and the column head. So I will simply delete this constraint. Also, I'm going to delete the structural point. We do not need it anymore. And I am going to use the connection type link between a structural line to a point. In the dialog box, I will simply enter a group number being equal with the number of the bridge deck. Then I will select the direction to be in the global X direction. I will enter an axial bedding stiffness with a value of 1 on the power of 6 kilonewton per cubic meter. Then I need to select the source structural line. So I will select both of my structural lines and hit the enter. And then I need to select the target structural point, which will be this one. And the springs are being generated. Now you need to repeat this procedure in the global Y and in the global Z direction. And then you also need to define a torsional spring about the global X direction first, with a stiffness value of 1 on the power of 6 kilonewton meter per radian. And again, you need to select the source structural lines and the target structural point. And there you go, the torsional springs are also generated. When you are ready with the definition of the 3 translational springs and the 3 rotational springs between the structural line and the structural point, the look of the connection will be similar what you can see on the screen now. The reason why you need to split the circular shape into two half circles is that otherwise the connection would be recursive since you have a closed circle. And of course the form of the structural line always follows the contour of the cross section. So for my rectangular shape 600 by 800 cross section, I should create 4 structural lines following the contour of the cross section and generate the springs between the structural lines and the structural point. After having rerun the analysis with the applied springs. Now you can see that the design error disappeared from this region. So the design of the quad elements at this location was now possible. Going back to SOFi+, I'd like to show you an alternative solution for the other column head. So let's just zoom in to the other column head and apply a different solution here. What you can do is simply delete the point-to-point constraint and instead of it just apply a point-to-point spring element. So you need to go to the structure element tab and there choose the point-to-point link option or command, and if I click on it I need to set up again 3 translational springs in the 3 global coordinate system direction and also 3 torsional springs against the rotation about the global x, y and z axis. The stiffness of the axial and the torsional springs needs to be chosen carefully. If they are given with a too high stiffness value, then again this location will attract a lot of bending moment. However, if they are too weak, then it might lead to instability of your structure. So you really need to play with the stiffness value of the springs to find a reasonable solution to be able to get rid of the high peak values in the bending moment, but on the other hand also keep the deflections in a normal range. I'm suggesting to start off with a value between 1 on the power of 4 and 1 on the power of 5 kN per cubic meter for the axial springs, and also the same magnitude for the torsional springs. So all you need to do is just enter a group number, a direction, for example global x, and a value which is going to be equal with 1 on the power of 4 at the beginning, and then you need to click on the new button to create a new axial spring, again in group number 10 for example, and the value of the spring constant will be 1 on the power of 4 in this case, and the direction will be the global y. And you need to repeat this procedure by adding new springs in the axial direction and also against the rotation. When you are finished with the input of the springs, you should see 6 elastic link tab in this dialog box. As you can see, 1 for the axial spring in global x direction, 1 in the global y direction, 1 in the global z, and then 3 torsional springs about the global x, y and z direction. Now all you need to do is just simply click the first point of this point link and then the second point of this point link, and then the springs will be generated. Okay, now I will terminate the command, export the model to SSD, rerun it and see if the results are better, meaning that the peak bending moments disappeared and the design of the quad elements were possible. After having rerun the model and reviewing the results in WinGraph, one can see that I was just partially able to solve the problem. The bending design problem disappeared, but some quad elements are still failing against shear. In this case you need to go back and fine-tune the spring constant of the defined spring between the structural points. This is an iterative procedure and sometimes it is very time-consuming, but still better than the original layout when between the 2 structural points a rigid coupling was defined. Now let's go back to SOFi+ and talk a little bit more about the 2 other problems that can happen in this type of bridge. As I mentioned at the beginning of this video, there could be a problem at the intersection of the vertical wall and the wing wall. When you first perform the design of the quad elements of the wing walls, you can visualize the design error of the quad elements in WinGraph as we saw previously. You can locate the part of the wing wall that is failing, and what you need to do is the following. In reality, these high peak values cannot be developed since the concrete material will crack. So this is what we are going to mimic also with our simple solution. I will just simply create a new material whose E modulus is going to be set to a quite small value, and I'm going to create an attribute area over the part of the wing wall that is failing in the design. In the properties of the attribute area, I'm going to set the new material with the small E modulus. This will allow the internal stresses to redistribute into other parts of the structure. Okay, now let's execute the aforementioned workflow, starting off by cloning material number 1. So all you need to go is head over to the materials, select the first material, right-click on it and choose the clone option from the drop-down list. By doing so, all you need to do is enter the new number of the new material, which is going to be 11 in my case. When the cloned material is defined, we need to adjust its E modulus. So I will simply double-click on the material number 11 and the material dialog box will open. And in here, I need to edit the value of the elastic modulus. And normally I take the hundredths of the original value, which is roughly 350 megapascal or Newton per square millimeter in this case. Then I will simply hit OK to accept the changes. All we need to do is adjust the UCS coordinate system of the SOFi Plus to be able to define the attribute area. To do that, I'm going to use the AutoCAD command UCS, which creates a new coordinate system for me, and I'm going to click the intersection point of the wing wall and the vertical wall. Then I need to click once more to point the X direction, which is going to be, in my case, the longitudinal direction of the wing wall. And then I need to click for the second time to be able to define the direction of the y-axis. If our temporary coordinate system is defined in this way, we can now head over to the structural elements, on which tab we are going to find the attribute area option. I'm going to simply left click on it, and a new dialog box, the definition of the attribute area, will appear. This dialog box is very similar to the definition of the structural areas. All you need to do in this dialog box is changing the property what you would like to alter on the structural area. As you can see, you can change the general properties, or you can change the meshing properties, the support or bending properties of the structural area, or the geometry, so the stiffness of the structural area. Now we simply would like to change the material of the structural area over a certain patch or over a certain area, which can be found on the General tab. Here you can see I can change the materials, either the area material of the structure area or its reinforcement. Now I'm going to choose to change the material of the area itself, and instead of material number 1, I'm going to use material number 11. The multiple ways how one can define an attribute area can be seen down in the command line. In this case, I'm going to select the rectangle type of definition and draw a rectangle from the intersection point of the wing wall and the vertical wall, roughly in the magnitude of the cracked section. So let's say that this is the area, this is the patch on the wing wall that is going to crack. And now I'm going to simply terminate the command by pressing the escape button. By finishing off the definition of the attribute area, we have provided a patch on the wing wall where the E modulus is reduced quite significantly to enable a stress redistribution in the wing wall at the vicinity of the intersection of the vertical wall and the wing wall. The remaining problematic part that I haven't mentioned yet how to solve is again the intersection of the vertical wall and the bridge deck. Usually on the vertical wall along the edge, the quad elements are undesignable. The way how you can avoid this is exactly the same what I just presented for the wing wall, namely to create attribute area along the edge over a certain height where the quad elements are undesignable. Having said that, basically that's all what I can offer or recommend to avoid these peak values in the bending moment diagrams at the problematic location of this type of bridges. I hope you enjoyed watching the videos. If yes, please show it with a thumbs up and see you in the next video. Bye!